14th one, we have a look at that. Yeah, 14th A part. Okay. 2 meter scales, one of steel and the other of aluminium, agree at 20 degrees centigrade. Calculate the ratio of the aluminium centimeter and steel centimeter at 0 degree centigrade. So 0 degree centigrade. So you aluminium and you steel at 0 degree centigrade. We can take it as they agree at wherever they agree, that is what we can take as the initial temperature. And I am putting 1 minus because this is temperature is getting reduced. The 11th, which one are you talking about? This is the 14th one. So at 20 degrees centigrade they agree. So this will be like if you put 20, I am putting, or you can say plus minus 20. So you can put aluminium and steel and see what is the ratio. So if you do that, do you get the answer or what is the problem? This is the initial one. Initial is 20 degrees centigrade. That there we are. They will agree on that. You may call it U20 if you want. And this is the new. This is that 0 degree centigrade. This is the new temperature. So that minus 20 will be the required answer. So if you do that, does the answer come out or what? See, they agree at 20. So at 0 you have to find. So U0 will be U20 1 minus alpha delta T. Delta T is minus 20 because from 20 you have to go negative 20 to get 0. So this is the aluminium and steel lengths at 0 degree centigrade. So if you substitute, do you get the answer or not? Is there any problem with that? Yeah, are you getting that? Shall we go for the 26th question? As I am doing it, both these questions will get answered. Strain is when a force acts and a body is stretched. That is called strain. Change in length per unit length. In this case, it is thermal expansion which is happening due to heat. See, if you are pulled apart, if you are stretched, then you say there is a strain on you. But if you have grown tall or you have grown broad, that doesn't mean there is a strain. It is a natural growth. So strain is only when a force acts and you are pulled apart. So we will see that. Okay, so here the strain is, there is no strain in this question. It is thermal expansion, so we take it as 0. These two, the 30th question also will get answered as soon as we do this next section based on thermal stress. So let's see. This next idea, I'm calling, we are doing the topic called thermal stress. But before we do that, let's talk about something. You see, I'll deal with that later. Let me define certain things. Now, if you have a wire there, and it has a natural length, which is, let us say, L0, and then you hang some weights on it. So when you hang some weights on it, this wire will get stretched. There will be a change in length. If it's a steel wire, then also there is a change in length. In a rubber band, we are very clear that you can pull it like that. That's what we call the rubber band. It's elastic band. So there is a tremendous change in length there. The change in length per original length is called as strain. Delta L by L is strain, or to be precise, it is called longitudinal strain. Longitudinal strain. Now, if you remove the weights, this wire will snap back to its original position. The property of a body to recover its original shape is called what? Elasticity. That is your elasticity. So the wire has elasticity. Rather, why does the wire go back? Because there is a certain force involved here, and this area of cross section we can call as A. So the force which comes up when a load is put on it is called as stress, or to be precise, in this case, longitudinal stress. The restoring force per unit area which comes up is called as the stress. So every substance or every material has a particular property, that is the stress by strain ratio, or again to be precise, the longitudinal stress to the longitudinal strain. This ratio is called as Young's modulus. Why is Young's modulus? It's a property. This is the measure of elasticity. What will be the unit of stress? Newton per meter square or Pascal. And what about strain? It will be dimensionless. So Young's modulus will also have a unit of Newton per meter square or Pascal. That's right. Which is more elastic, steel or rubber?
Steel.
Why are we saying that? Okay, yeah, because the measure of the elasticity is Young's modulus and not strain. Although normally we say rubber band and show like that. So many of us may feel that elasticity may be to the amount of stretch. No, the strain is more for rubber. It is not the strain which is the measure of elasticity. It's the ratio which you can have. That which has a high Young's modulus will have a higher elasticity. Okay, fine then. Yeah, the range beyond it is not elastic, so let us not talk about it. We are only talking about in the elastic region. Okay, anything on that you will study in the properties of materials, so we are not getting into that. I am talking about right now this, because this concept is to be used for thermal expansion, so only that much which we require. So here, we can define Young's modulus as stress by strain. So I can say F by A delta L upon L, so it becomes like this. FL by A delta L, that's your formula. We can say it like that, or in an alternate version we can say stress equals Y times strain. Sometimes the extension delta L, we can put it as X, the extension, change in length. So the stress looks like this. This or this are one and the same. F by A is Yx by L. Now, when you write it like this, we can equate it to the formula of a spring. In a spring, what happens? Just take down this formula. I just want to rub off certain things here and derive a new formula there. See, in the case of a spring, what do you do in a spring? In case of a spring, we say that when you stretch it, if the extension is so much, we say there is a force which is equal to minus kx. F equals minus kx. This is the restoring force which comes in a spring. What is the potential energy stored in a spring when you stretch it by x? Half k x square. Now, parallelly, just look at this formula. Here also we can say this formula we can rewrite as F equals YA by L times X. If I want, I can put a negative sign showing that extension is downwards and restoring force is upwards. So a negative sign is also not out of place. Now if you compare these two, the YA by L looks like X, and rather it is X. In a spring you can see the spirals, and here it is like molecular springs. In this wire which you don't see the spirals, but think of them as molecular springs, and all the molecules are trying to pull it back. So it is the same idea. So here, what will be the potential energy of the wire? Half K, half YA by L times X square. It should be the same. The same analogy is being used. Now, here I do some manipulation. What is the, now divide this by volume of the wire, divide by A and L. If you divide by A and L, AL is the volume of the wire. This can be called potential energy per unit volume. I take it as small u. Potential energy becomes potential energy density. And what do you have here? This AA cancels. Sorry, I've cancelled the X. The A cancels and this is the L. So what you have is half Y X by L the whole square. This is nothing but half Y strain square. And Y times strain is stress. So you can get it as half into Y, not Y, half into stress into strain. This is the formula for elastic potential energy density. Elastic potential energy density, this is the formula. You have it here. So, the new formulas that we have got is like the F by A is Y delta L by L, or this is one formula we have got, and that's another formula we derived. So remember the two boxes. We have derived this formula afresh. This is the background for elasticity, which I now use in thermal expansion. Let us see how we do that. Now, consider that we have a rod kept between two walls, you have a rod between two walls, and we heat up this rod. Now if you heat up this rod, now you have not allowed any, when I'm saying rod, if it is a small wire, the wire will buckle itself. But this is a rod, so it cannot buckle. Think of it like this. There is a, and you are heating this rod. Now this rod cannot bend or fold. It will be like that. So what will happen if I increase the temperature? Now think of it. What would happen if this wall were not there? If this wall were not there, this would have expanded like this. Of course, I am exaggerating the length of expansion, but that's the idea. So how much would this expansion be? The thermal expansion would have been delta L is how much? Alpha L delta T. Can we say that? Alpha L delta T will be thermal expansion. But now, the wall does not allow it to expand, so you can think of it as if the wall pushed it back to its place. The wall compressed it. So we can think of it like that, that it expanded thermally and the wall compressed it back. The mechanical compression was equal to the thermal expansion, and that's the reason why this rod does not look expanded. We can think of it like that. So now in the previous case, we have just now done for Young's modulus that the stress equals Y times strain. Okay. Now if you pull a wire, that is Young's modulus. The Young's modulus can also be applied for pressing a rod. Now there delta L is compression. Delta L can be extension or delta L can be compression. If it is extension, you will have tensile stress. If you have compression, you will have compressive stress. That's all. The formula is same. So here, what can we say? What will be the compressive stress on this? The compressive stress on this will be Y times the same formula, delta L by L. Now this is your delta L. Now this time delta L refers to mechanical compression. So let me call it mech compression upon L. This is your strain. But according to this, mechanical compression is equal to thermal expansion. So this becomes alpha L delta T. So this stress equals Y alpha delta T. This stress, you don't see any visible force here. It is only that the rod was trying to expand and the wall says no, you cannot do so. This stress is called as thermal stress. We are calling this as thermal stress because it has been born because of thermal reason. So the rod is not allowed to expand, and because of the greater temperature is trying to expand, there will be a stress inside that rod. If you do this with a glass rod, for instance, the glass rod will be compressed. At a higher temperature, it will break down because the glass cannot take. Glass is brittle, it cannot take that stress. Yeah, are you asking something there?
So in the denominator, shouldn't it be L plus alpha L delta T, because the length should have been L plus?
Yeah, you are right, and it doesn't matter whether I take L or not because this ratio is going to be near about same. If you talk very exactly, yes. But this ratio, if you calculate, it is going to come out to be the same. So hence we neglect it. Okay? You are right in saying that exact length should be L plus alpha L delta T. Okay? But when you calculate, since this length is pretty small, this ratio is going to be the same as this by this. Yeah, is it fine? The thermal stress F by A is Y alpha delta T. Now let's see some question based on this. So consider this question. Coming up next, we have a composite rod between the two walls. Let's see what happens. So let's say this rod is L1 alpha 1, has the properties L1 alpha 1 Y1, and this rod has a property L2 alpha 2 Y2. So these are the walls between which the rod is locked up. Now this is the junction J. This is the junction J. So what happens when you heat it? This junction shifts. So we have to calculate what is the shift in the junction. We heat it up and maybe the junction goes to the right. I'm not saying necessarily goes to the right, but it might shift. So now, this is the junction afterwards. Let's call it J dash. So your junction has shifted by X. Well, my question is, what is X? That's what we have to find out. With the given, in the terms of the given parameters, L1 alpha 1 y1 and L2 alpha 2 y2. Why does the red rod contract? I want some discussion on that. Do some loud thinking. Whatever you're doing, tell me. What is the red rod contract? Is the red rod having thermal contraction or something? See, one of the rods may expand more and another may expand less. That's understandable. Why is the red rod contracting? And is X equals, does X equal thermal expansion? That's another question of mine. Does X equal thermal expansion?
No.
What is X?
Difference in thermal expansion.
Difference in thermal expansion of both the rods?
Yes, sir.
The red rod is not expanding, so how can you say it is red rod's thermal difference in thermal expansion?
So basically the force at that point has to be balanced.
Which rod exerts a greater force on the other rod? We have seen that the blue rod has expanded by X and the red rod has contracted by X. So what is this X? Is this thermal contraction or some other phenomena is also happening here? Like, how do I deal with that? Because unless I know what's happening, how do I put a formula there? So tell me what's happening. You haven't answered my question. Who is exerting a greater force on the other? Which rod?
Blue rod.
Blue rod is exerting a greater force on the red rod. Have you done Newton's third law? किसी भी पॉइंट पे इक्वल होगा, उस पॉइंट की क्या जरूरत है? Action equals reaction. If blue pushes the red, won't the red push the blue? Can the blue push the red more than the red pushes the blue? Can I push the wall more than the wall pushes me? Why is the wall pushing me? Because I am pushing the wall. If I stop pushing the wall doesn't push me. Action equals reaction, no? And here the cross-sectional area is same. I didn't say that, but you can see that the rods are of the similar area. So, what can you say about stress on the blue rod and the red rod? What can you say about stress on the blue rod and red rod? Blue is great, less, equal to, insufficient information.
It must be equal.
It has to be, yeah, I think you had initially said blue and then you kind of got that action equals reaction, so it has to be equal. The stress is same. The stress is same throughout. So I'm asking you, if X is not thermal expansion, what is X? Is there something other than thermal expansion happening here? Yeah, it is happening. Aren't the blue and red pushing each other? Blue is pushing the red like that, red is pushing the blue like that. Both are elbowing each other. And one of them seems to win. Both of them are struggling for the same space. So both of them are pushing each other. So what is going to happen is mechanical contraction as well. Thermal expansion and mechanical contraction, both the things are happening. So if you look at, for the blue rod, X is, what can I say X equal to? If both phenomena are happening, X equals what?
Thermal expansion minus mechanical.
Exactly. Thermal expansion minus mechanical compression. So shall I say for rod 1, this is thermal expansion minus mechanical compression. What is thermal expansion equal to for the blue rod? Delta L equals alpha 1 L1 delta T. Can I say that? And what is mechanical compression equal to? From the formula, F by A equals Y delta L by L. What is delta L? Delta L equals FL by AY. Can I say that? So how should I say it here? What should I write? Dictate. F by A
Y alpha delta T.